Hello everyone, thank you so much for viewing this video. Before we get started with discussing the contents of the video, I wanted to introduce my nonprofit, the Accelerated Training Program. Our vision is twofold. First, we want to expose all marginalized groups to cybersecurity education, as well as removing the systemic exclusion of cybersecurity education to marginalized groups. Our website is www.t-atp.org. And if you would like to partner or want to learn more, please visit our contact page where you can fill out your name, your email, and a message, and we will get back to you. And again, thank you so much for viewing the contents of this video. Please check out the nonprofit when you have a moment, and let's get to the video. Hello, and welcome to day 21. Have yourself a merry little webcam. Let me start the machine now while I'll be reading. The machine could be loading up, booting while I'm reading. Okay, so let me start the attack box as well. And it's going to be split screen. If it will come on. Okay, great. Okay, so let's start reading and let's get to it. Okay. After investigating the web camera implant through hardware and firmware reverse engineering, we are tasked with identifying and exploiting any known vulnerabilities in the web camera. Elf McSkitty is confident you won't be able to compromise the web camera as it seems to be up to date, but we will investigate if there are off-the-shelf exploits that are needed to take back control of the workshop. So, what are we going to learn? Explain Internet of Things, why it's important, and if we should be concerned about their dangers. Understand the difference between an Internet of Things specific protocol and other network service protocols. Understand what a publish subscribe model is and how it interacts with Internet of Things devices. Analyze and exploit the behavior of a vulnerable Internet of Things device. Okay, so what is an Internet of Things? The Internet of Things, or IoT, defines a categorization of just that, things. Devices are interconnected and rely heavily on communication to achieve a device's objectives. Examples of Internet of Things include thermostats, web cameras, and smart fridges, to name a few. While the formal definition of Internet of Things may change depending on who is setting it, the term can best be used as a broad categorization of a device that sends and receives data to communicate with other devices and systems. If Internet of Things defines such an extensive categorization of devices with varying capabilities and objectives, what makes them important or warrant that we study them? While several justifiable reasons exist to study Internet of Things, we will address three possible answers. First, Internet of Things categorizes unique devices. Again, examples, smart fridges that don't match other categories such as mobile devices. Internet of Things devices tends to be lightweight, which means that the device's functionality and features are limited to only essentials. Because of their lightweight nature, modern features may be left out or overlooked, one of the most concerning being security. While we live in a modern era of security, it may still be considered secondary, which is why it is not included in core functionality. Second, devices are interconnected and often involve no human interaction. Think of authentication in which a human uses a password for security. These devices must not only be designed to communicate data effectively, but also negotiate a secure means of communication such that human interaction is not required. So, for an example, using a password. Third, devices are designed to all be interconnected. So if device A is using X protocol and device B is using Y protocol, it presents a significant problem in compatibility. The same concept can be applied to security where devices are incompatible but could fall back to insecure communication. Remember, security is often thought of as secondary, so not ensuring a device can securely communicate with other devices may be a fatal weakness that is overlooked or deemed less important. Okay, so in the next section, we will cover how Internet of Things protocols function and study examples of how these devices may or may not pro- um, address flaws. Okay, so Internet of Thing protocols. So this is categorized as any protocol used by an Internet of Thing device for machine to gateway, or machine to cloud communications. As previously defined, an Internet of Things device sends and receives data to communicate with other devices and systems. With this in mind, an Internet of Things protocol's objectives should be efficient, reliable, and secure data communication. We can break up Internet of Things protocols into one of two types: an Internet of Things data protocol or an Internet of Things network protocol. These types may be deceiving in their name as both are used to communicate data. However, they differentiate in how and where the communication occurs. At first glance, an Internet of Things data protocol commonly relies on the TCP/IP transmission control protocol over Internet protocol model, and an Internet of Things network protocol relies on wireless technology for communication. So we'll continue expanding the purpose of these protocols below. Okay. So if we break down the Internet of Things data protocol into concepts that we're familiar with, an Internet of Things data protocol is akin to common network services we interact with daily, such as HTTP, Web is Life, SMB, FTP, and others. In fact, HTTP can be used as a backbone for other Internet of Things protocols or as an Internet of Things data protocol itself. Again, that's why Web is Life. An Internet of Things network or wireless protocol still maintains the same goals as data protocols, that is, data communication, but it achieves it differently. Rather than relying on traditional TCP protocols, these protocols use wireless technology such as Wi Fi, Bluetooth, Zigbee, and Z Wave to transfer data and communicate between entities. So, throughout the task, we will focus on the former category of protocols and how they interact with Internet of Things devices. Okay, so let's delve deeper into Internet of Things data protocols and why it's a data protocol. Okay, messaging protocols and middleware. Okay, because data communication is the primary objective of Internet of Things data protocols, they commonly take the form of messaging protocols. That is, the protocol facilitates the sending and receiving of a message or payload between two parties. Messaging protocols communicate between two devices through an independent server called middleware, or by negotiating a communication method amongst themselves. So, devices commonly use middleware because they might be lightweight and efficient. For example, an Internet of Things device may not support a more robust protocol such as HTTP. A server is placed in the middle of two clients who want to communicate to translate the communication method to a means both devices can understand. So here's an example. So we have middleware, which is an independent server, and client A is like, hey, I want to use this internet protocol. I'm going to send this to the middleware. The middleware is like, okay, I'm going to send the HTTP data to client B. Client B is like, yo, I have this HTTP data. I'm going to send it to you, independent server middleware. And the middleware is like, bet. I'm going to send the Internet of Things protocol back to client A. So, as we mentioned, the compatibility of device protocols could be problematic. Middleware fixes some of the associated issues, but may still be unable to translate all communications. So, here's some popular messaging protocols below. So, MQTT, which is what this room is using, message queuing telemetry transport. And so this is middleware, and this is a lightweight protocol that relies on a publish subscribe model to send or receive messages. So this again is one of the objectives: publish and subscribe. Okay. Co-op constrained application protocol translates HTTP communication to a usable communication medium for lightweight devices. AMQP, Advanced Message Queuing Protocol, acts as a transactional protocol to receive, queue, and store messages, payloads between devices. DDS, Data Distribution Service, a scalable protocol that relies on a publish subscribe model to send or receive messages. HTTP, hypertext transfer protocol. So now this is device to device. The other four above was middleware. Used as a communication method from traditional devices to lightweight devices or for large data communication, and WebSockets. Again, device to device relies on a client server model to send data over a TCP connection. Okay, so we'll delve deeper into MQTT for this room. Okay. Functionality of a publish-subscribe model. So messaging protocols commonly use a publish-subscribe model, notably the MQTT protocol. The model relies on a broker to negotiate published messages and subscription queries. So let's look at the diagram. So we have a publisher, and the publisher says, hey, I'm going to send a message to you, broker. The broker is like, okay. So I'm going to send the message from the publisher to the subscriber. And the subscriber is like, hey, broker, are there any more messages? If so, send them to me. Okay, so again, step one, a publisher sends their message to a broker. So that's this arrow here. Step two, the broker continues relaying the message until a new message is published. That's this arrow here. Step three, a subscriber can attempt to connect to a broker and receive a message. That's this arrow there. The protocol should work fantastically if a single broker is needed for one device's objective. But what if several types of data need to be sent from one device or several publishers and subscribers need to connect to one broker? Using more than one broker can be feasible but increases unnecessary overhead and server usage. A secure communication method should also ensure the integrity of messages, meaning one publisher should not overwrite another. To address these problems, a broker can store multiple messages from different publishers by using topics. A topic is a semi-arbitrary value pre-negotiated by the publisher and subscriber and sent along with the message. The format of a topic commonly takes the form of name, ID, function. When a new message is sent with a given topic, the broker will store or overwrite it under the topic and relay it to subscribers who have subscribed to it. So below is a diagram showing two publishers with two different messages and its associated topics. So we see publisher A is like, hey, I have this message A, B, C, D, and it's under topic A. Send it to the broker. Publisher B is like, yo, I have a message 1, 2, 3, 4. It's under topic B. Send it to the broker. Now, the subscriber is like, okay. The broker sends message A, B, C, D to subscriber A, and subscriber A is like, hey, am I subscribed to topic A? If I am, give me the message. And then with subscriber B, the broker sends message 1, 2, 3, 4 to subscriber B, and subscriber B is like, hey, am I subscribed to topic B? If so, send me the message. Okay. Note the asynchronous nature of this communication. The publisher can publish at any time, and the subscriber can subscribe to a topic to see if the broker relayed the message. Typically, subscribers and publishers will continue attempting to connect to the broker for a specific duration. We should now understand the functionality of this model, but why is it important for an Internet of Things device? A publish-subscribe model is helpful for any data maintained asynchronously or received by several different devices from one publisher. A common example of a publish-subscribe model could be a thermostat publishing its current temperature. Several thermostats can publish to one broker, and several devices can subscribe to the thermostat they want data from. As a protocol, MQTT is lightweight with a small footprint and minimal bandwidth. Because remember, with Internet of Things, you have a limited computing power. So you can't bring the world with you. You have to make sure whatever you're using is small and it doesn't have a big overhead. Okay. Are Internet of Things protocols inherently vulnerable? Okay, so we've identified the relation between Internet of Things protocols and network services and how messaging protocols function. This still leaves the question of how secure Internet of Things protocols are. Okay, so let's start applying what we're familiar with. HTTP. HTTP vulnerabilities often referred to a vulnerability in the software application built off the protocol. This does not mean protocols are absent of vulnerabilities, but they generally possess strict requirements and require revisions before release or public adoption. Similarly, Internet of Things protocols are not inherently vulnerable. So, what makes an Internet of Things device insecure? So, before we give a more formal explanation, let's consider the default settings of MQTT when it's first deployed. So, a broker assigns all devices connected to it read-write access to all topics. That is, any device can publish and subscribe to a topic. This may seem okay at first. In the thermostat example, we are only communicating temperatures, so the integrity of the data should not be an issue. But let's delve further. Okay. Our data should follow CIA, confidentiality, integrity, and availability best practices as closely as possible. That is, data should not be read or manipulated by unauthorized sources and should be accessible to authorized users. Following best practices, authentication authorization should be implemented to prevent potentially bad actors from compromising any principle of the CIA triad. Okay, so what are the risks to Internet of Things devices if best practices are not considered? Risk is almost solely dependent on the behavior of the device. So let's say the device trusts an MQTT publisher and parses data or commands to perform actions affecting the device's settings. An attacker could send a malicious message to perform unintended actions. For example, a thermostat sends a message with a specific format to a broker, and a subscriber parses the message and changes the temperature. An attacker could send their message outside of the intended application, for example, a mobile app, to modify the device's temperature. Although this example may seem modest, imagine the impact this could have on other devices with consequences or critical devices, which are essential to function in a society or economy. Okay, so to recap, an MQTT instance may be insecure due to improper data regulation best practices. An instance may be vulnerable if the device's behavior allows an attacker to perform malicious actions from expected interaction. Okay, the differentiation between insecure and vulnerable. An insecure implementation may allow an attacker to exploit a vulnerability, but this does not mean the implementation is inherently vulnerable. So, in our next task, we'll expand on this idea and attempt to identify methods we can use to identify behavior of a given device. Ooh, starting to get into hands on, getting close to it. Okay. Before moving on to the hands on section, darn, I thought we were there. Let's address how we can modify or identify information about device behavior. So, we've defined that Internet of Things devices are vulnerable because of their application's behavior. So, let's briefly look at how we can analyze the behavior and see if we can find entry points that can be abused. So, an attacker can use communication sniffing, source code analysis, or documentation. What are those? Communication sniffing determines the protocol used, the middleware or broker address, and the communication behavior. For example, unencrypted HTTP requests are sent to a central server, which are then translated to co-op packets. We can observe the HTTP packets and look for topics or message formats that vendors should hide. So examples are settings, commands to interact with the device. Source code analysis. Okay, can give you direct insight into how a device parses sent data and how it's being used. Analysis can identify similar information to communication sniffing, but may act as a more reliable and definite source of information. Documentation provides you with a clear understanding of the standard functionality of a device or endpoint. A disadvantage of only using documentation as a means of identification is that it may leave out sensitive payloads, topics, or other information that is not ordinarily relevant to an end user. So, now, okay, once a behavior is identified, we can use clients to interact with devices and send malicious messages or payloads. To cement this idea, let's go back to our thermostat example. Okay, so most Internet of Things devices have a device ID. We did that in the last room with the firmware. We learned Santa found the device ID. that is used to identify themselves to other devices, and that other devices can use to identify the target device. Devices must exchange this device ID before any communication can occur. In the case of MQTT, a device ID is commonly exchanged by publishing a message containing the device ID to a pre-known topic that anyone can subscribe to. So it's like, hey, here's my device ID. This is a common topic. And it's like, I'm publishing it here. And it's like, everyone has access to the topic. So if you want to know my device ID, go here. Once an attacker knows the device ID and behavior of a target device, they can attempt to target specific topics or message formats. These topics may trust the message source and perform some action blindly. So, example, change the temperature, change a publishing destination, etc. Okay, in our scenario, preliminary information has been identified by Recon Red through hardware analysis and firmware reverse engineering. The web camera device is known to use the MQTT protocol, and we have a list of potential topics we can target. So, but before we can analyze these potential vulnerable topics, we need to understand or interact with the MQTT endpoint. So, let's learn how we interact with MQTT. So, different protocols will have different libraries or other means of interacting with them. For MQTT, there are two commonly used libraries we will discuss. That is Pi-hole and Mosquito. Pi-hole is a Python library that offers support for all features of MQTT. Mosquito is a suite of MQTT utilities that include a broker and publish subscribe clients that we can use from the command line. Okay, so we're going to learn the functionality. Okay. Subscribing to a topic. We'll use the Mosquito sub client utility, and what we can use is the dash T or dash dash topic, and the topic is called device ping. So we're saying call the Mosquito sub client, and then we're going to go subscribe to the topic device ping. So we can also specify a broker using the dash H. So we're saying, hey, we're using the broker example.thm for a topic device THM. Okay, publishing to a topic. So we'll use the dash M or dash dash message, and that's to publish a message to a topic. So what this is saying is, hey, we're publishing to the broker example.thm, the topic device info, and we're sending the message, this is an example. So for both clients, there are several notable optional flags. Okay, so dash D is debug message, dash I or dash dash ID specifies the ID to identify the client to the server. Dash P or dash dash port specifies the port the broker is using. So in this case, it's 1883. Dash U or dash dash username specifies the username for authentication. Dash uppercase P or dash dash password is used to specify the password for authentication. And dash dash URL used to specify username, password, host, port, and topic in one URL. Okay, a device using MQTT will craft messages as a means of communication authentically. As an attacker, we will attempt to portray our publishing source as a legitimate source in hopes that the other side will interact with the message as it would an authentic message to provide us with unintended behavior. So we're going to use the practical application. So I've already started the machine and the attack machine. So the device, as we covered briefly, the device interacts with the MQTT broker to publish and subscribe to predefined topics. The device broker is found at 10.10.106.105. From firmware reverse engineering, we found that there are two topics. Device int publishes the device ID of the current topic, and device ID command subscribes to the device ID specific topic to receive commands and settings. The device is known to use RTSP, which is real-time streaming protocol for input streaming. If an attacker can control where and how the RTSP stream is forwarded, they can redirect it to an RTSP server they control. Okay. The device ID command topic can specify behavior through a numeric CMD parameter and the ability to parse a key value pair to be used to interact with the device. Okay. We do not yet possess how the command topic behaves or the format it is expecting. Okay, it is up to us to craft a malicious message to target the command topic. So if we're looking for a challenge, here's a code snippet. So let's look because again, why not? I like a challenge. Okay, so this is written in Python. So we have a function subscribe client MQTT client. Another function on message. We have client user data and message. So our payload, we get the message payload and we decode it. The topic, we get the topic from the message object, and we print the topic payload and parsing payload. So then with the payload, we take the curly brackets and we remove it along with we split on the comma. So if I had to guess, it's curly brace client curly brace URL, but we'll see. Okay, so the command, okay, we have 0 and 1. So the command payload is in payload, which is here. This line, these lines here. So the command payload is in the first place and the first section of the payload. So this is a array. So the first section, the first entry, this is the command payload. The URL payload is in the second because with arrays, the index starts at 0. Okay, so the command payload is in the first placement. The URL payload is in the second, and so we print the command and URL payload. So it looks like we have a target command of 10. We define these variables: command name, command value, URL name, URL value, and so we set them to 0 and 1. Next, what we're doing for the command payload, we're splitting on the colon. The URL payload, we're splitting on the colon, the second entry. If command payload is lower, so if the name equals command, and if the payload, the command value equals the target command, then we have a match. So if the URL name is URL, and we're going to print RTSPS URL match, and then we're going to print the value. And then next, what we're going to do is we're going to try to execute the URL text. This X means execute. And then we're going to write the URL payload, the value, and then we're going to close the file. And if that doesn't work, we're going to open the file, and then we're going to write to it, and then we're going to put in the URL value, and then we're going to close, and then it's going to call this update.sh. Okay, so if I had to guess, I would say that the format is command URL. So let's see if I'm right. Yep, command URL. Yeah. So I explained it a little, like looking at the code and how to parse. It was a very quick way of doing it. I've done Python before, so I knew what to look for. But again, if you've done one programming language, the syntax might be different, but the semantics or what you're doing is the same. So again, I just did a guess. Okay, we're going to get back to finishing room 21. IoT, we need to get the flag from the RTSP stream. So what I'm going to do first is I'm going to open a terminal. And for question 1, I guess for the Mosquito port, it said during the reading it was 1883, so I tried it. But I tried to use Nmap and it was taking over an hour and still wasn't completing. So I used the hint here, and we're going to use this. And the thing that I didn't have the SCSC and the min rate of 1500. And this is to make the scan go faster. So let's do that now. So in map, SCSV, IP 10.10.198.113 VV for verbose, max min rate 1500. Okay, so we see ports 80 and 22, and port 1883 is going to show. Because we are this is an Internet of Things device that is that has Mosquito installed. So 1883 is going to show up. So let's wait a little bit. Oh wait, I messed up. It's not going to find it because you see here it's only looking at 1,000 ports, and so 1883, this is the 1,000 common ports. 1883 is not a common port, so I need to add dash p dash, and so that means it's going to check all 65,535 ports. You see that here, 65,535 ports, as opposed to our first one that was looking at 1,000. So yes, we had to add the um where is it? The dash p dash to do all ports. Okay. So this finished. And what do we know? We see port 1883. So we were correct. Okay, is the device init topic enumerated by mmap? Yep. Okay, what version? 1.6.9. Okay. So, and we see this next to it is our device number. We also can do that by, let's open a tab, and we're going to say mosquito sub, and we're going to go here, and we're going to say dash H, and we're going to put in our IP address 10.10.198.113. The IP address to the for the Internet of Things, and then we're going to do our topic, which is device init. And give this a couple seconds. And yep, you see we have it. This alphanumeric here matches that there. So again, just showing different ways that you can find it. So this is our device ID. So when, for instance, if we had other Internet of Things devices and it wanted to interact with us, it will pass in this device ID to say, hey, I want to interact with you. Okay. So now we need to, we found the device ID. Now we need to start the our TSP. So I want to say docker run rm network equal host. I'm basically just copying what is here. Okay. So we see on TCP it's on port 8554. That's our listener. On UDP it's on 8000. So it's listening now. And if this didn't work, we could set up a TCP listener, but we don't need to do that because this worked for us. So now I'm going to open a new tab. I like working in different tabs just in case if I need to go back and follow my thinking. It just works better for me. So we're going to say Mosquito Pub because we're going to publish. And we're going to say, let's see if I could copy. Yeah, I'm going to copy this. Paste. Um, Hold on. Dash T. And we need to do device. And our ID is here. Copy. Which also matches there. Paste. Command. And so this is the command that we're looking for. So what I'm going to say, and remember to publish, we're going to need the dash M. We're publishing to a topic. Okay, so let me explain. Publishing, so this is our broker, which is the IP for the Internet of Things. This is our topic device, our device ID command. We're going to do a message dash M, and we are going to type command, and our value is 10. So if we want to overwrite or redirect, that's 10. And then, wait. Okay. Our URL, and we're going to say the value is RTSP. And our attack box, 10.10.171.131.8554, which matches the TCP, the RTSP listener on TCP. And our path, I'm going to say test 25. I'm just making up a path. And I'm going to close that, and I'm going to do that. Oh, wait. This isn't going to work. Okay. So we needed a command here. That's in quotes. We put in a number. That's why that's not in quotes. So any string is in quotes. URL. Okay. I'm going to say enter. Okay, hold on. Did it? Okay, did it not pick up? Okay, let's say test 3. Okay, RTSP 10.10.171. Oh, 31. I thought it was 131. Okay. Looks like that's still okay. 10.10.198. Is there something I'm missing? Okay. The URL is our attack box. So that's 10.10.171.31. 8554. Okay. Okay. Device. Da-da-da. Message. Wonder. Hmm. Okay. Publish Mosquito Pub 1010 198 113. The device. Okay. Oh, okay. So it's there. Oh, so it took a minute. Okay. So we see here a connection on 1010 198 113 was open. Okay. It just took a while. Okay. So test three here. Okay. I'm just going to delete this. So I think I had to use double quotes. Okay. So it's here. And we can see because we'll start seeing dropped packets, and that's what we're seeing. So these packets are being lost. Now, what we okay, so explaining what happened. So a connection on 1010 198 113 was open, and it created this here with port 6328, and it published to the path test 3, excuse me, which is what we have here. So now what we can do is let's open a new tab, and we can say VLC RTSP 127.0.0.1 8554 test 3. Okay. And look, we got it. So this is what it was. THM, your camera is mine. Oh, all right. So we were able to effectively redirect output to our attack box, and we're looking at it. So we were able to effectively hack into the web camera. Okay, so if we want to learn more, we can check out command injection in the vulnerability research module. Oh, this is so cute. Elf, the camera is mine. That's so cute. So yeah, so we're actually the real time stream. Oh Lord, what is this? Hold on. Real time streaming protocol. Yeah, so we were able to publish to the topic here, and then we created a path of test 3, and we were able to open it in the VLC. And yeah, so the camera is theirs. So the elf's on the camera. So that was fun. That was really cute. That was really fun. So I can't wait to see you in the next day's lesson. Again, we're super close to Christmas, so I wonder what Bandit Yeti is going to do to try to steal it. Try his last hurrah of stealing Christmas. So have a good day. Bye.